lecture of week 4. And this week we are, second. So our week 4 lecture, designing or design of lecture members, part 1, the moment capacity. So design of lecture members, part 1, moment capacity or flexural capacity of beams. So the flexural capacity is our first part, and the requirement from you this week is to get familiar with the concept of effective section. Z effective. The effective section is due to the local buckling behavior of the member, as you know. And we need also to get familiar with the concept of the lateral torsional buckling for flexure member, or we can call it global buckling. So for flexure member, we have two type of behaviors. One of them is the local buckling behavior, and this will be considered in the section moment capacity. It's the same concept like the compression members, and we have also global buckling behavior or overall buckling behavior or lateral torsional buckling behavior. This will affect our member moment capacity. And then we will need to get familiar with the different restraint type on beams, because restraint will affect the global buckling behavior. So the global buckling behavior is mainly affected by the restraint of the beam. So the restraint means the lateral supports of the compression or the critical flange, which will affect our global buckling behavior. And we need to also be able to calculate the section and member capacity, moment capacity of the steel flexure member according to the Australian standard AS4100. And section 5 of the standard is covering the flexure member or design of flexure members. So let's have a look on the outline for the lecture or the flexure member design. The first part is the local buckling behavior, which affecting the section moment capacity for bending about principal axis, which is covered by section 5.2 in the Australian standard. So if this our cross section, so we are studying the moment about the flexure, the principal axis, or we are studying MX. So mainly we are studying bending or flexure behavior about the principal axis X. And we will also study the flexure torsional buckling and the lateral beam restraint, section 5.42, 4.4.2, and then the member moment capacity of the beam with full lateral restraint, section 5.3. So we have two main type of member moment capacity for two type of beams. The first type of beam is beams with full lateral restraint. This is covered in section 5.3. And we have also member moment capacity for another type of beams, which is beams without full lateral restraint, which is covered in section 5.6. So we can summarize that we have to discuss, or we know, the section moment capacity, then the member moment capacity for different type of beams with different type of restraints. One of the types is the full lateral restraint beam, and the other type is beams without full lateral restraint. So let's have a look on the standards and the requirement of the standard. So for the flexure member design, and again, just a reminder that we are designing hot rolled steel flexure members. So we are still in the first part of our course, so we're still in the hot rolled steel, which is covered by AS4100. Okay, so the design criteria in the standard is two design criteria. One of them is the section moment capacity, considering the local buckling behavior, and member moment capacity, considering the global buckling behavior. So if we go to the standard, section 5.1, to design a bending, like a beam or a flexion member under bending moment, the applied moment or the design moment, M asterisk, should be less than or equal to values. One of them is phi msx, which is the section capacity, and phi mbx, which is the member capacity. So if our design moment m asterisk satisfies these two conditions, so our design is okay. Where mx asterisk is the design bending moment about x-axis. So as we mentioned earlier, our focus in this part is design of beams like I-beam, like this one, subjected to mx. So if this our cross section, so our focus is mx. That's why m asterisk is m asterisk x, and we have msx and mbx. And phi is the capacity factor from table 3.4 in the section 3, and phi for steel members, all of the steel members, is phi equal to 0.9. So for members, 0.9, for connection, it may differ. Okay. MSX is the nominal section capacity as per clause 5.2, we will see now. MBX is the nominal member capacity as per 5.3 or 5.6 for the bending about X. So MX asterisk is the design moment. This comes from analysis of the beam. So like if you do your structural analysis, you will find the moment applied to the beam. So this is M asterisk X. MSX, this is the section moment capacity. MBX, this is the member moment capacity. So our design criteria or our design condition, M asterisk is less than MSX and less than MBX, and we need to apply the factor of safety 5. So let's start our section moment capacity calculation. So the section moment capacity is MS. This is covered by section 5.2. For the section moment capacity for bending about the principal axis, again, this is our principal axis XX, so this is our moment MX. So the nominal section moment capacity is MS equal to MS equal to F yield Z Z effective. So MS, section moment capacity, equal to F yield, the yield strength of steel, times Z effective, the effective section modulus. So F yield strength of steel based on the type of steel you are using, and Z effective is the effective section modulus. Okay, effective means, if you know effective, why effective? Effective to consider the local buckling behavior of the member. So where ZE is the effective section modulus, and we will know now how to find it using clause point 5.23, 5.24, and 5.25. And to find the section modulus, the effective section modulus, we need to find the slenderness ratio of the section. Okay, so just before we start, we go to this part. So MS equal to F yield times Z effective. Z effective is our effective section modulus considering local buckling behavior. Okay, so if we look to this slide here, I have a question for you. Why we should calculate Z effective, not Z, for section moment capacity? So the answer is because of local buckling. So local buckling in the compression and the compressive plate element of the flexure member will reduce the moment capacity of the member. So if you look to these two types of cross sections, both of them under moments, under bending moments, here but also under bending moments. This bending moment, any bending moment, if this our x-axis, so the bending moment cause what? Can you tell me? Tension on one side and compression on the other side. So this means that this part of the member, this part of the section is under compressive stress. So the part of the member under compressive stress will be susceptible to local buckling. So if you can see here, here is how the local buckling affect our member. Just for like the the C section, for the C section, and it is like horizontally aligned, and this one is also C section vertically aligned. So you can notice the local buckling of the flange, top flange. Again, only the compression flange will be susceptible to local buckling. So we need to find Z effective because of the local buckling of the compression plate element or the compression flange. Okay, so Z effective to consider the local buckling behavior. The main thing is in the critical or compressive flange. Okay, how can we find Z effective? This is our next step. To find Z effective, we need to find the section slenderness. So the section slenderness, lambda S or lambda effective, shall be taken as the value of the plate slenderness, lambda effective, for the element of the cross section which has the greatest value of lambda E divided by lambda EY. So we need to find lambda E for web and flange. Then we compare and take the critical one. If the critical one is web, we take the web. And if the flange is critical, we take the flange. Then we compare with the limits. So after you got lambda effective, you need to compare it with the limits for lambda effective. We have lambda EY and lambda EB. So lambda effective yield and lambda effective plastic. So let's firstly, we get lambda effective first. Lambda effective equal to B divided by T root F yield divided by 250. We have seen this before in the axial compressive member. Same concept. Lambda EY will be the plate element yield slenderness limit, which we will see now. B is the clear width of the element outstand from the face of the supporting plate. T is the element thickness. So the first step to find Z effective is to find the slenderness ratio lambda E. So we need to find lambda E for web and lambda E for flange, and we will select the critical of them. So lambda E will be B divided by T root F yield divided by 250. Here as well, B over T root F yield by 250. Here, if you are calculating for web, this will be B web, T web. If you are calculating for flange, so just B flange, T flange. And for F yield, if F yield different for web and flange, we need to find F yield for web, F yield for flange. So this is our first part to find lambda E and lambda E for flange. Okay, so again, this step, we need to find the section slenderness ratio lambda E. So lambda E equal to B over T multiplied by root F field divided by 250. So after we got lambda E for web and flange, we need to select the critical. After selecting the critical, we need to compare with the limits. What is the limits for slenderness ratio? So the limits will be found in table, find table 5.2. So table 5.2 will give us the limits for lambda E. So the two limits we need are lambda EB and lambda EY. So lambda EB is the plastic limit for lambda. Lambda EY is the yield limit for lambda. So we will go to the table 5.2, and if, for example, if we have a flange, so the flange is, if this is our flange, so the flange is supported from only one end. So this part for flange. So for flange, if it is under uniform compression, so we need to check what is the residual stress type. So the stress type, the residual stress type can be found, or the key is here. So if you have a hot rolled section, so it is HR, for example, here. So the limits will be, if you have hot rolled section, so 9 and 16. If you have welded section, like the example we have in previous class, so this means that the limits are 8 and 14, for example. So based on the residual stress, and if you are designing or finding the value for flange or web, where is the web? Web is a member that supported in both sides, from both sides. So if we are still in the broad flange section, so this is our web. So web is supported in two both sides or both edges. So this is the web. So for the web, again, if you are heavy welded, so it is 30 and 35. If you are hot rolled, so hot rolled here, so you have 30 and 45. So this is the limits. So after all calculation now, we know lambda E from the previous step, and the limits lambda EY and lambda EB from this table. So the next part will be the check. So after we found the value of lambda effective and the limits, we need to compare to know if the section is compact, non-compact, or cylinderness or cylinder section. So we have three cases. So let's put this here. After we got lambda E for web and lambda E for flange, we will work only on the critical one. So let's assume one of them is critical, this one for example. How we know this is critical? We will find, if you go back to the standard here, so the standard mention is we need to find the cross section that has the greatest lambda E over lambda EY. So we will need to find lambda E over lambda EY for web and lambda E over lambda EY for flange. And if the web is critical, this means this value is the greatest. If we just to make assumption here. So if this is the greatest of the two, so we will work with the web. So this means that we will consider lambda E for the web equal to our lambda S. And then we will use this value to compare with the two values from the table, lambda S yield and lambda S, sorry, lambda, yes, lambda S yield and lambda SB. Lambda S yield will be lambda EY for web and lambda EB for web. So the idea is we have two members, web and flange, web and flange. So we need to work on one of them. So we will work with which one of them? The one with the greatest percentage of lambda E over lambda EY. Then we will use this value to decide if the section is compact or non-compact or cylinder. Okay, the three cases are, so our section, our cross section based on the value of lambda E, lambda S of the member can have three options or three cases. The first case is we may have compact section. The second is non-compact section. And the third is cylinder section. Okay, compact section means no buckling will happen or no buckling will occur. And cylinder section buckling will occur. Non-compact is in between, so something in the middle between no buckling at all and between buckling occur. Okay, so the standard give us how to decide if the section is cylinder or compact or non-compact. So let's have a look here. So when we consider the section is compact, when lambda s is less than or equal to lambda sb. Okay, based on our example, we consider this for web. So for the web, just have a question. Thank you, Abu Salah. We're still working on that, but compact section means no buckling, so this is the best thing you can get. Okay, so we will design based on if the section compact or non-compact or cylinder. We don't need to change the section now. So now at this stage, we just need to know if the section compact, non-compact, or cylinder, because the calculation will be based on that. Okay, if we go back just one step back, why we do all of that? We do all of that to find Z effective. So Z effective will be different value for compact section, different value for non-compact section, different value for cylinder section. So we need to know if the section is compact or non-compact or cylinder to find Z effective. Is it clear now? Do you have any question, guys? Any other question? Okay, so how can we know if the section is compact or non-compact or cylinder? So we compare the value of lambda we got from the calculation. In this example, we assume it for web. If we found it less than lambda SB, so this means the section is compact. Let's have an quick example here. For example, if you are using this web, so how much is the plastic limit? 30. So if our lambda is 25, for example, this means the section is compact. Okay? The other option is if lambda is, so here we have lambda is less than the plastic limit. If lambda is more than the yield limit, so this means if we have lambda is more than or more than lambda is yield for the web. This means the section is cylinder. Because this is the two extreme cases, that's why I start with them. So if lambda is more less than lambda is plastic, so it is compact. If lambda is more than lambda is yield, it is cylinder. Anything in between will be non-compact. So for non-compact, we have lambda s is less than lambda s plastic and sorry, more than lambda s plastic and less than lambda s yield. So if we have lambda s more than lambda s plastic and less than or equal to lambda s yield, again for the web in our assumption, so this means the section is non-compact. If we go to the table, Let's assume that we have three cases. Case 1, lambda s equal to 25. Case 2, lambda s equal to 50. Case 3, lambda s equal to 40. So 25 less than 30. So the section is compact. 50 is more than 45. So the section is cylinder. 40 is between, something in between here. So it is non-compact. So after we know lambda s, we can decide if the section is compact or non-compact or cylinder section. So what is the consequences of the type of the section? If the section is compact, again we mentioned that no buckling will happen. If the section is cylinder, so buckling will occur. And for the non-compact, something in between. So if the section is compact, the section modulus ZE will be the lesser of two values, S, the plastic section modulus, or 1.5 Z, the section modulus from the table. So Z effective in this case will be the lesser of two values. One of them is S, the other one is 1.5 Z. Have you used the tables before for the sections, the cross sections? Have you? We have used the section table. I just will show you the, yes. Thanks, Bernard. Brendan. So if we have a look to the tables, for example, for a universal beam section, can you see it clearly? Okay, for any section, let's start with this one, for example. We have properties about Z. So properties about X, sorry. So we have ZX. So for this section, how much ZX, for example? This value. And if you look beside it, what you have? SX. So this is S that we mentioned in the formula. So you will have to select between two values for this member as an example. So our Z effective will be the lesser of 1.5 times 3230 and between 3680. And we will select the lesser of this. So this is what is meant by the compact section. And how much is Z for this compact section. For a non-compact section, or let's start with the cylinder section. For a cylinder section, Z effective equal to Z from table ZX multiplied by a ratio of lambda sy divided by lambda s. Is this value, is this percentage more than 1 or less than 1? What do you expect? It is less than 1. This is a reduction factor. So this value is less than 1. Because again, lambda s is more than lambda S yield. Okay, for a non-compact section, it is like interpolation between the two. So for non-compact section, Z effective equal to Z plus lambda Sy minus lambda S divided by lambda Sy minus lambda Sb multiplied by Zc minus Z. Okay, what does Zc means? Zc for a compact section. So ZC is Z for a compact section. So let's write it again here. So for non-compact section, because this is a complicated one, lambda S in this case more than lambda S plastic and less than or equal to lambda S yield. So Z effective in this case will be Z plus lambda Sy minus lambda S, lambda S yield minus lambda S, and this is multiplied by ZC minus Z, and here we have lambda SB minus minus lambda SY minus lambda SB. So this is like interpolation between the two values for cylinder and compact section, where ZC is Z for compact section, which is the lesser of S and 1.5 Z. Z is section modulus from table Zx. Lambda S is the cylinderness ratio of the we used for web or flange. In our example, we mentioned web, and those series are the slenderness limits. Okay, so if we know all of this, we can now find Z effective. So after this calculation, you need to decide if the section compact, non-compact, and cylinder section. Then you will find Z effective. Do you have any question about Z effective for this part? No? So after that, the final step will be, after you know Z effective for all the section, MS will be F yield time Z effective. So our problem in the section capacity was only to find Z effective. So Z effective will be one of these cases. Case 1, case 2, case 3. Okay, after we know the section capacity, the second criteria will be the member moment capacity. So the member moment capacity or the overall buckling of beams. So member moment capacity considering the global or overall buckling of beams. In beams, when we apply vertical load to the beam will be susceptible to lateral torsional buckling. So if you look to this beam, the original beam position is A, and after the loading, due to this beam is only restrained at the support here and at the support here. So due to that, the beam has moved laterally to position number B. So position A is the original position. Position B is after buckling. So can you see how the lateral torsion buckling affect the beam? So this will affect the moment capacity of the beam because the beam already started buckling. The factor that influence the lateral torsion buckling behavior or the global buckling behavior is the flexure stiffness of the beam, the torsional stiffness of the beam, the unsupported length of the beam, and the restraint. The unsupported length means L unsupported or L unrestrained is the distance between the two supports or the restraints. Okay, we will see this in the calculation in the formulas, but this how the beams is affected by lateral torsional buckling. And in this slide, this is some example of the lateral restraints that can be provided for the beam. And the main rule of the restraint is to prevent the flexural torsional buckling of the beams, or in bracket, the lateral deformation of the beam. So in beams, we are worried about the lateral deformation because the lateral deformation causes the flexural torsion buckling or lateral torsional buckling. Some of the supports that can be supporting or preventing the flexural torsional buckling is the slabs, for example, concrete slabs. So the concrete slab, because the beam will be connected to the concrete slab, so the concrete slab will provide restraint so that the beam will not be able to move laterally. Another option is the lateral is this beam connected to the top flange. So this beam will provide lateral and torsional restraint to the beam. And for this one, the beam is not providing like torsional support, but it only provide lateral support. Okay, this also another example of the support. So we have connected two beams together with some braces. So these braces will provide lateral supports for the compression flange. So our main problem is the compression flange. So we need to provide lateral restraint for it. Okay, so this is our some examples of the restraints of the beams. And now let's have a look on how the lateral restraint affect the type of the section. So as we mentioned earlier, our member moment capacity is affected by the global buckling or the lateral torsional buckling. And to prevent or to provide some stability, we need to have lateral restraint. So the lateral restraints will affect our member capacity. So that we need to consider the lateral restraint. According to the lateral restraint, we may have different type of beam. Some beams will have full or fully restrained or fully laterally restrained. Some beams will be partially restrained. Some beam will be laterally restrained only, and some beams will be rotationally restrained, and finally unrestrained. So these are the five types of beams according to their lateral restraint. So the standard cover all of that and give us some instruction how to consider any of them. So the standard here discussing the fully laterally restrained sections. So the section can be assumed fully restrained if the restraint or the support effectively prevent the lateral deflection of the critical flange. So the main problem again is our critical flange. If the restraint prevent the lateral deflection, so we can consider it as fully restrained beam. So as a designer, you need to assess if the beams if the support or the restraint prevents the lateral deformation or the lateral deflection of the critical flange or not. This is the first part. Second part is also effectively prevents the twist rotation of the section. So we have two criteria to consider it as fully lateral restraint. So we have lateral deflection and twist rotation. If the restraint prevent these two, so we can consider it as full. Okay, so the prevention can be effectively or fully and also partially. So for the twist prevention, it can be fully restrained or partially restrained. And the standard give us some examples here. So in this example here, as you can see, we have this is our beam and the if this our moment, so the compression flange is supported by this member, and this member preventing the lateral deformation or the lateral deflection of the beam. Okay, and because also the bottom flange is supported with a similar member, so this section will not be able to twist. So because the beam is supported by this members, so it is not able to laterally restrain or twist, so that we can consider the beam is fully restrained. And this member should be along the beam to be considered as fully restrained. So if this beam is continuous, so this member is continuous with the beam. Okay, so this means each point of the top flange or the critical flange is prevented from lateral deflection or twist. In B, we have the same thing here, but here because of the if you look here, so because we don't have the member at the bottom, we have only one member at the top. So this member will allow for some twists. So this member here will prevent the lateral deflection and allow for some twist. So it prevents the twist, but not fully because this member is flexible member. If it is rigid member, so if it is a rigid member, it will fully prevent the twist. But because it is flexible, so it doesn't prevent the twist. But the standard mentions that if it is partially prevents the twist as well, so we can consider it as fully restrained cross section. And here is the critical flange definition in the standard. So we can consider the flange is our critical flange if it is if there is no restraint at that section, and the flange will deflect the farthest during buckling. So the critical flange if this our member is the flange that can buckle during the load. So for example, if you have only a support here, whatever the support is, let's say only one support here and one support here. So any point here can move laterally. If it can move laterally, so this is an unrestrained part, or this is our critical flange. Okay, so the critical flange is the flange that, or any point that can move laterally during buckling. So this for fully lateral restraint. Another case for the fully lateral restraint is here. So the restraint or support effectively prevents lateral deformation and effectively prevents the twist of the section. So again, effectively prevent the lateral deformation and effectively prevent the twist. And the example here is similar to the example we had before here, but instead of a flexible member, we have a stiff member. So this is a stiff member, so it prevents lateral deformation, no lateral deformation, and no twist. So we can consider this a fully restrained member as well. So we have two cases for lateral for fully restrained member. A is prevent effectively the lateral deformation and the twist. And here as well, prevent the lateral deformation and prevent the twist rotation of the section as in this example. Okay. So this is fully restrained members. For the laterally partially restrained, number 2, the member can be partially restrained. In this case, a cross section may be assumed partially restrained if the restraint or the support effectively prevent lateral deflection of some points in the cross section other than the critical flange, and partially prevent the twist rotation of the section. So if the restraint, prevent the lateral deformation of points rather than the critical flange. So if the restraint prevents the lateral deformation of point rather than the critical flange, so we can consider this as partially restrained. Okay, this means that this is our critical flange here. So C indicates the critical flange. Okay, so just to make a clarification on the previous one, here as well is C is the critical flange. So I will repeat this one again, sorry. For the fully restrained cross section, case number 2, the restraint or support effectively prevents the lateral deflection of some other point in the cross section and effectively prevents the twist or the rotation of the section. So here, the stiff member prevents the lateral deformation of some points rather than the critical flange. Okay, so we can consider this as fully. The difference between the partially and fully is here we have the member is flexible. So if the member that prevent the lateral deformation is flexible, so we can consider it as partially restrained, not fully restrained. Okay, so the two cases are quite close, but just the difference is the member or the restraint is flexible or stiff. If the member is stiff, so we can consider is fully restrained. If the member is flexible, we can consider it as partially restrained. Number 3 is laterally restrained cross section. So we have two lateral deformation. We have two deformation to prevent lateral deformation and twist. In the previous cases, so I have a question. Would a Berlin count as stiff or flexible member? We consider it as stiff because it's also the Berlin is supported by or is strengthened by the sheeting. Okay, thank you. So if we look to the lateral, if we look to the two deformation we need to prevent, so lateral deflection and twist. In all the previous cases, we have like prevent part or full the lateral deflection or the twist. Here in this type, laterally restrained cross section, the standard mentions that the cross section of a segment whose ends are fully or partially restrained may be assumed to be laterally restrained when the restraint effectively prevents the lateral deflection of the critical flange. So if this is our critical flange and this member is preventing only the lateral deflection, so we can consider it as laterally restrained cross section. So we have no twist restraint. So this means we will prevent only the lateral deflection, but we cannot prevent the twist. So if we prevent only the lateral deflection, we can consider it as laterally restrained beam. Number 4 is rotationally restrained cross section. So again, we have two deformation, lateral deflection and twist or rotation. So what you expect in this case? In this case, we will be able to prevent the twist. Sorry. We will be able to prevent the twist, but we cannot prevent the lateral deflection. So lateral deflection is allowed, twist is prevented. So a cross section of a member which may be assumed fully or partially restrained may be assumed to be rotationally restrained when the restraint or the support provides significant restraint against lateral rotation of the critical flange. So if we prevent the lateral rotation of the critical flange out of plane, so this is considered as rotationally restrained cross section. So no restraint for the lateral deformation, but we have a restraint for the lateral torsion of the critical flange. So this means that we may consider it as rotationally restrained cross section. And here is some example of the rotationally restrained cross sections. Okay, so if we have a moment connection between these two members, moment connection means rigid connection. So the rigid connections will prevent the rotation of the member or provide a part of the like restraints. It will provide restraints to the members. So the effective length of the member will be at this point, for example. So this part only, or this part only, the critical member, because the other part is prevented from rotation due to the rigid connection. Okay. So this all the cases you may face in your design. And the last case is unrestrained cross section. So unrestrained cross section, for any cross section of member which doesn't satisfy any of the previous clauses. So it is not fully or partially or laterally or rotationally restrained. So we can consider it as unrestrained. So if it doesn't satisfy any of the previous, so we cannot prevent any movement of the critical flange or the other flange, so we can consider it as unrestrained member. So similar to this figure, figure 5.4.1. So if this our critical flange, so the flange can rotate, twist, and can also deflect. If the flange can rotate and deflect, so this means that both deformation are allowed. So this member is unrestrained member. Okay, so this is our unrestrained member if it doesn't satisfy any of the previous, and we cannot prevent the lateral deflection or the twist. Okay, they went 5 minutes of break, and we meet again at 10:20. Is that okay? Yeah, we have a break for 5 minutes. Okay, Abu Salah? See you in 5 minutes, guys. Okay, guys, can we continue now? Good. So this is an example of lateral restraints for a beam. So beam segment between two adjacent lateral restraint. So if this our beam in elevation and this is our beam in plan. So for example here, this point here is no lateral support, so we can consider it as U or unrestrained. And here at this point here, we have type of support can be fully or partially restrained based on if the rotational or sorry if the twist and lateral deflection is prevented or not. So at the support, as you can see, as the vertical support, the lateral support may be one of two cases, fully or partially, based on if the lateral deflection and twist are totally prevented or not. Okay, here for example, at the middle here, if we have, for example, purlins or secondary beams running perpendicularly to this beam, so we can consider this as fully or partially support as well. Okay, in the last case is this two. This two support is lateral only support because they are on from one side only. So we can consider them as lateral only support. So this means that we can have different type of lateral support for the beam. So we need to assess what is the deformation is prevented and what is not prevented to decide if it is fully or laterally or partially unsupported. Okay, so now after we know the type of lateral strain, so we need to start calculation of the member capacity of the members. So we will start with member capacity of segment with full lateral restraint. So if the section or the beam with full lateral restraints, so we have two of them. We have segment with continuous lateral restraint and segment with intermediate lateral restraint. A segment with continuous lateral restraints may be treated as having full lateral restraint provided that both ends are fully or partially restrained. The continuous restraint acts at the critical flange. So this means that if we have a beam running like this, so this means the whole beam in this case in the continuous lateral restraint is prevented from lateral deformation. This will be in the case if we have a concrete slab above this beam. If we have a concrete slab above this beam, this concrete slab will provide full lateral strain to the compression flange. So to consider the beam or the segment with continuous lateral strength, we need to have both ends are fully or partially restrained, so the end is full or partial, and the continuous restraint acts as at the critical flange. So this means that this flange should be our critical flange. So this C. Okay. So this will be in cases of concrete slabs connected to the beam. Another type is segment with intermediate lateral restraint. A segment with intermediate lateral restraints, close 5.4, that divide the segments into a series of subsegments may be treated as having full lateral strain, provided that both ends are fully or partially restrained, so similar to this one here. The length of each subsegment satisfy close 5.3.2.4. The lateral restraint acts as the critical flange. So these two are here, but we have another case if the length of the subsegment satisfies the next slide. So in this case, we don't have not continuous lateral restraint. So similar to the above, but not continuous. So this condition here satisfied by this part. So segment with full or partial restraint at both ends. So this case and like case 5.2.3.2.3 and 5.3.2.4 are sharing the length condition. So a segment with full or partial restraint at both ends may be treated as having full lateral strength provided the length satisfies L over Ry plus less than or equal to 80 plus 50 beta m multiplied by root 250 by F divided by F yield. So this for the case of segment of equal flange I section. So if we have equal flange I section, so use this formula. Another formula, but different parameters here, 60, 80, 50, 40 for equal flanged channel. So if it is I-beam, use the first one. If it is channel, use the second one. Where Ry is the radius of gyration about the minor principal axis Y. The ratio beta m should be taken as one of the followers. Beta m can be -1, -0.8 with for segments with transverse load. So if you have a beam and we have not only vertical load, we have also shear load or transverse loads. Number 3 is the ratio of the smaller to larger moments in the length L, positive when the segment is bent in reverse curvature and negative when the bent in single curvature for segment without transverse loading. So if you have, I think you have seen this before, if you have M1, M2, and M1, M2. Can any of you help me with that? So this case we have single curvature. This case we have double curvature. So these two cases, let's make the moment like that. So in this case, this is a deflected shape, and the standard give us M1 and M2. Here M1 and M2, and this is double curvature. So this is called single curvature. This is double curvature. So beta m here equal to beta m here equal to. Can you help me in a few? Do you remember this part or this value of beta m? Beta m is the ratio between what? Between m1 to m2, considering that m1 is small, largest moment. So m1 is the smallest, m2 is the largest. But the idea is, what is the sign here and here? Do you know which one is positive, which one is negative? Have you seen this before in steel and timber course? If you studied steel and timber, nothing. I just want to know which beta m is positive and which beta m is negative. So Kingsley, you mentioned that single is negative, so double curvature will be positive. Do you agree with that? Okay, thank you, Brendan and Kingsley. Okay, so beta m, this is what is mentioned by the standard here. So beta m can be taken as -1 if the moment is same value. So when beta m equal to -1, when m1 equal to m2, so this means that we have only one moment. So in this case, you can take beta m as -1. Otherwise, we will need to follow the following. So you have M1 and M2, one of them small, one of them large. So this percentage is less than 1, should be less than 1. If it is single curvature, the sign is negative. If it is double curvature, it is positive. So after all of this, so here we know the member is fully, if it is fully, if it is a segment with fully lateral restraint, so we need to make sure if it is continuous lateral strain or intermediate lateral strain so that we can know the formulas for the next part. So here the member capacity for segment without lateral restraint. Just before we go here, just what is the member capacity of segment with full lateral strength here? If we make sure that it is fully restrained. Okay, so just to quickly here. So for members with fully lateral restraint, when satisfying the conditions before, we consider that MB will be equal to MS. So for member with fully lateral restraint, the member capacity will be equal to the section capacity. Okay, so this means that we are not expecting global buckling of this member. So now we jump to the final part, how we find the capacity of the members without fully lateral or without full lateral restraint. So for the segments, fully or partial restraints at both ends. Okay, so this means that if this our members, so they are only supported or laterally supported at the ends. What this means? This means that this members can laterally deflect in this direction. Okay, so this will be open section for open section with equal flange. This what is the case we're focusing on. So for open section like universal beam or universal column section or broad flange channel, these are all open sections. The member capacity MB will be this formula. So MB equal to alpha M times alpha S times the section capacity and should be less than or equal to the section capacity. So for the member capacity, we need two factors. For the member capacity, we need two factors to find the member capacity. We need alpha M and alpha S, where alpha S is slenderness reduction factor. MS is the nominal section capacity. We found it earlier, section 5.2. Alpha M is the moment modification factor. We will see how to find alpha S later, but alpha M is one of the following values. Alpha M can be taken as 1 or a value of or value from table 5.6.1 or alpha M equal to 1.7 M asterisk M divided by the root of M asterisk 2, M asterisk 3, M asterisk 4 and alpha M should be less than or equal to 2.5 where M asterisk M is the maximum design bending moment in the segment. M2 and M4 are the design bending moments at the quarter point of the segments. M3 is the design bending moment at the midpoint of the segment. Okay, so for example, if we have a beam like this one, so we have we will need to divide two quarters to find M2 and M3 and M4. Okay, let's leave this for the example, but the formula is alpha m equal to 1.7 m asterisk m divided by the root of m2 asterisk plus m3 asterisk plus m4 asterisk. Just checking something. Okay, we just made squared here. So this m asterisk 2 squared, m asterisk 3 squared, and m asterisk 4 squared. Okay, so I just need to update this one. So this for lambda for alpha m. Then alpha s, the slenderness reduction factor alpha s, will be calculated according to alpha s equal to 0.6 root ms divided by MOA squared plus 3 minus ms divided by MOA, where MOA is equal to MO or M naught, where M naught is the reference buckling moment. So MO is the reference buckling moment. So the reference buckling moment means this is the moment when the section will start buckling. So it is like the critical buckling moment. Okay. So this is MO, and this is our value for MO. The reference buckling moment MO equal to by squared EIY divided by L effective squared times GJ plus phi squared by squared EIW divided by L effective squared. So M naught equal to this formula here. So we have E and G are steel properties. We have IY and IW and J are section properties, and we have L effective is the effective length of the beam. So if we know all these properties or these values, we can find the buckling reference moment. So E and G is the elastic moduli. I, Y, J, and IW are section constant. LE is the effective length of the section. And here is table 5.6 for alpha M. If you want to find it from the table 5.6.1 based on the moment on the section. So according to the moment distribution, can come to this table. So for example, if we have for example this one in a frame, let's assume this one. So how much is alpha m? Alpha m will come from this table. So alpha m will be this value or this value. The first value 1.13 plus 0.12 beta m. If beta m between 0 and 0.75, the other value is negative 0.238 plus 4.8 beta m if beta m between 0.75 and 1. So according to the moment distribution, we can come to this table to find the factor alpha m. So alpha m can be three values, one or value from the table or using this formula according to the moment distribution. So the moment distribution will decide which value to take for alpha m. For some cases, like cantilever beam, if we have a cantilever beam, so the segment will be unrestrained at one end. So if we have cantilever beam, I have to read the first column. Here, I mean this slide, Kingsley. Yeah, here we have like a beam or part of a frame with a uniformly distributed load W, and we have two moment at the ends. Here, for example, we have beam with one concentrated load. Here we have beam or part of the beam with two moments here, one moment here and one moment here. Okay? Is it what is the arrow? You mean for the first one? This and this are the reactions. Is it okay? Yeah, because x here is a support. So if this is a support, so you may have reaction. If it is not support, so you will have shear from the adjacent parts of the frame or the beam. Okay, so let's go to our case again. If we have cantilever, like universal beam or universal column as I section. So this I beam is what fix it at one part. So it is fully restrained at this part, but at the edge it is free. So if it is free at this edge, this means that this part is unrestrained. So for the cantilever beams, it will be segment unrestrained at one of the ends. The ends that it is not restrained is the free end. Okay, so the formulas will be different for this part a little bit, but same concept. So the member capacity will be so the nominal member capacity MB for a segment unrestrained at one end and at the other end is fully or partially restrained or laterally continuous restraint shall be the following. So MB equal to lambda s, alpha s times ms. So MB equal to alpha s ms less than ms, where alpha S in this case equal to 0.6 ms divided by MOB to the all to the power 2 plus 3 minus ms divided by MOB, where ms is the nominal section capacity determined in accordance with clause 5.2 for the cross section, and MOB is determined by elastic buckling analysis. This one option, or we shall take in M.6.11 with MOI equal to MO obtained from equation 5.6.1.3 and the appropriate value of alpha M. So we have two options. One option is to use the similar or the previous values as before. So we can use the previous values exactly as before and take alpha M from the table, not this table, but so for this one, we will again repeat this one. So lateral continuous or restraint against lateral rotation shall be determined using either equation 5.6.1.1 and point 2. These formulas are here, if you can see. So we will use 5.6.1.1 and 5.6.1.2. Where is point 1? So this is, we will use the same formula here and here. So similar to before, with MOA equal to MO obtained from section this one, and the appropriate value of alpha M from table 5.6.2. So table 5.6.2 is this table here. This 5.6.1 and this is 5.6.2. So in the cantilever beam, if we go back to our slide, so we can use either this option, the one below here, or the first option. So the first option is similar to before, but using table 5.2.6.2. So 5.6.2 give us the factors alpha M for unrestrained at one end, which is for cantilever beam. Okay, so for example, if you have fixed beam with one moment here, so alpha M will be 0.25. If you have fixed and one load here, so it is 1.25. If it is fixed and uniformly distributed load W, so it is 2.25. So these are the values for the member capacity of the cantilever. So the cantilever and the normal beam are same, using same for parameters, MB equal to alpha M alpha S MS, where alpha S for both of them is the same, and alpha M using this table for what? So this table for normal beams, and this table 5.6.2 using for the cantilever beams. So cantilever beams 5.6.2. And if we go back to the formula, we have one part we didn't mention. What is this part is? L effective. So L effective is the effective length according to clause 5.6.3. So the effective length will be according to this clause here, 5.6.3. So the effective length equal to this formula. L effective equal to KT, KL, KR multiplied by L. So L is the beam length, but we have three coefficient, 1, 2, 3. KT is the twist restraint factor given in table 5.6.3a. KL is the load height factor given in table 5.6.3b. And the last factor KR in table 5.6.3c, this KR. So the three factors KT, KL, KR are given in table 5.6.3 A, B, C. How to find KT? Start with KT. KT is the twist restraint factor. Can be one of the following values. We have three values, 1 or 1 plus this value or 1 plus this value according to the restraint arrangement. F means fully, L means lateral restraint, U means unrestrained, B is partial restraint. So according to the restraints, you will come to this table. For example, if your beam or your segment is fully restrained at both ends, so the factor is 1. If it is fully restrained and partially restrained at one end, so you can use this formula. If it is partially restrained at both ends, you can use this formula, where D1 is the clear depth between flanges, NW is number of webs if you have more than web, TF is the thickness of the critical flange, TW is the thickness of the web. So if this is our cross section, this is G1, and this is T flange, and this is T web, and number of webs is usually 1. So this is the value for KT. For KL, again, according to the restraints arrangement and the location of the load or the load height position. So if the load applied on the top flange, you can take from this table, from this column. If the load is applied at the shear center, so you can take it from this column. So what does this mean? For the open sections or the steel open sections, for example, let's do it with the flange. For the flange, we can have the load applied over the top flange, or at the shear center. So we can have case 1 or case 2. So the advantage of applying the load at the shear center is to avoid any eccentricity of the loading. So here, as you can see, when we apply the load on the top flange, we will have moments, additional moments due to applying the load here. But here, no additional moments. So applying the load at the shear center will provide or prevent any additional moments. The factor Kr, the last one, again based on the restraint arrangement. And if we have lateral rotational restraint. So if you have lateral rotational restraint, so you can find the value of Kr. If you have any or none or one or both. So you have four cases based on if you have lateral restraints or not. So this will affect the effective length of the beam. Okay? So if we know KT, KL, KR, we know L effective. If you know L effective here, you know M naught. If you know M naught, you can find alpha S. And from table, you already got alpha M. So if we know alpha S and alpha M, we can easily find MB. Okay? So all this explanation is to find alpha M and alpha S. If we know both of them, we can find alpha MB. Okay? Do you have any question, guys? This is if we are designing the restraint elements. So the restraint elements, the standard give us a condition of how much of the loads we need to consider for these elements. So the lateral restraint element shall be designed to transfer a transverse force acting to the critical flange equal to 0.025 times the maximum force in the critical flange of the adjacent segments. So we are designing the restraint to support 0.025 times the force in the flange. Okay, so this is just a hint about how to, if you want to design the restraint elements, how much forces you need to consider in this design. Okay, I think that's enough for our lecture today. Do you have any question, guys? I will see you in the class very soon. Thank you for attending and see you. Any question before we go? No? Okay, thanks.